Hello. For this video, we will be talking about the maximal flow problem. So please read through the basic sample that we will be using for the maximal flow problem. Suppose all the roads in the previous examples were changed to one-way roads instead of two-way, and furthermore, during the day, only a certain number of cars can pass through each one-way road. The question is how many cars should pass through which route or routes such that the number of cars traveling from city O to city T is maximum. So again, we will be using the same graph, maybe with different numbers. And what I'd like to do is I'd like to rotate this graph, okay? Such that the origin is on top and the destination is at the bottom. Now, to understand the maximal flow problem, instead of imagining these edges or arcs to be roads, what if these are pipes, water pipes? Okay, and imagine a faucet in node O and an exit pipe in node P. The maximal flow problem talks about opening the faucet in node O, letting water go through the different pipes, no? And eventually exiting in node T. If the number of, let's say, liters or gallons of water has reached the capacity in every pipe, imagine that the pipe will close down, meaning no more water can flow through that particular pipe. Okay? So the question is you open a faucet here, you let water go through the network pipe, you let gravity work its way until it reaches T. And the question now is how much water can go through the network. No? That essentially is what we call a um, maximal flow. Because you're trying to maximize the number of units that will flow through the graph. The solution method for the maximal flow problem is called the augmenting path algorithm. Before I show you the algorithm in itself, let me first define and discuss certain things that we need to understand, no? uh, so that we will be able to understand the algorithm. First, a residual network shows the remaining arc capacities or what we call residual capacities for assigning additional flow. What do we mean by this? For example, in the graph that we have between node B and node E, we actually have a one-way direction going from B to E with the capacity of 5. Now, given this arc from B to E with a capacity of 5, we can convert this into a residual network that will show remaining arc capacity. And what do we mean by that? This graph with an arc BE with a capacity of 5, when converted into a residual network, will actually show this. No? So first thing that you will notice is that we remove the arrows already. So there are no signs of direction anymore. However, we now have two numbers. One number is to the beside B, and the other number is beside E. What do these numbers represent? These numbers represent the remaining arc capacity. And what do we mean by this? The capacity of um, moving from node B towards node E is 5. And at the same time, the capacity of moving from E to B is a 0. Okay? So a residual network actually removes the idea of directions. However, to still include the concept of a directed graph, you now do it via capacities. You let the capacity of going back from E to be equal to 0. Now, once we have converted this arc into a residual network, the next thing we have to understand is this. No? If there is a flow of two cars from B to E, so given your residual network of 5, no, from B to E, if there is a flow of two cars, so you let two cars move from B to E, what will happen? Because you let two units or two cars move from B to E, then the capacity for you to move from B to E gets reduced by 2. So your 5 becomes 3. However, the capacity of moving back, no, from E to B now increases by 2. As you may notice, the sum of the residual capacities in an arc will always be the same. Because as you decrease in this capacity, you also increase the same in this capacity. Okay? Please do note that eventually it is possible to decrease the capacity here, or technically let at most two units move from E to B. No, technically that is possible because given this arc capacity, you are technically saying that you can let two units move from E to B. Now, how can you understand that concept with the fact that originally movement from E to B shouldn't be possible? Okay? So again, given that the arc capacity from E to B is now 2, therefore you can let two units move from E to B. But how do you juggle with the conflict where originally movement from E to B shouldn't be allowed? In this case, the way to understand why we can technically let two units move from E to B is because in the first place, you let two units move from B to E. And as long as the total movement from E to B is equal to 0, because in the first place technically movement from E to B is not possible, as long as the total, when you aggregate all the movements, no, uh, towards the end, as long as it comes out to be 0, then that should be okay. I hope this concept will be much clearer when we actually do the augmenting path algorithm later in the example provided. So given that the algorithm is called the augmenting path algorithm, let me define what an augmenting path is. An augmenting path is a directed path from source node O to destination node T in the residual network, such that every arc on this path has strictly positive residual capacity. Now, let us try to understand this definition by going to the example. Okay, so what I have here is the example, this example, but as you may have noticed, I've already removed the arrows. Okay, so because I've removed the arrows, I've included the arc capacity 0 to the movement of going back. No, so for example, because the arc in OA is a movement from O to A. Therefore, I place the arc capacity 8 beside O and the arc capacity 0 beside A. No? In the same way, I haven't finished everything here. If you look at OB, the arc capacity is a 7. Therefore, no? Therefore, if we are to convert it to the residual network, this should show a 7 and this should show a 0. Okay? And then, if we go back to the definition of an augmenting path, again, an augmenting path is a directed path from source node O to destination node T in the residual network. So in this network, such that every arc on this path has strictly positive residual capacity. So for example, given this residual network, I can say an augmenting path is no, O, A, T. Why? Because if you look at the residual capacity of O to A, the residual capacity from O to A is an 8, and the residual capacity from A to T is a 1. And every residual capacity is strictly positive. And therefore, this is an augmenting path. Okay? Now that you understand what an augmenting path is, let me now define what the residual capacity of the augmenting path is. The minimum of the residual capacities in the augmenting path is called the residual capacity of the augmenting path. Let me explain. Given that OAT is an augmenting path and 8 and 1 are what we call the residual capacities, then the minimum of these residual capacities, the minimum, which is in this case 1, no, is your what we call the residual capacity of the augmenting path. So this is technically the capacity of OAT at this particular point in time. Obviously, if things move, no, eventually, then the capacity of OAT might change. Okay, but at this point in time, where the capacity of OA is 8 and the capacity of AT is 1, then the capacity of OAT is 1. Now, this slide shows you the different steps in the augmenting path. You may pause the video in order for you to read the steps. However, let me give you a very quick pseudocode for this augmenting path algorithm. The augmenting path algorithm is actually easy to understand. All you have to do is first to convert your graph into a graph where the residual capacities are shown. Second, you identify an augmenting path. Third, you let the residual capacity of the augmenting path, no, move through the augmenting path, no, and you decrease and increase the corresponding residual capacities in the augmenting path. I think it will be easier to understand the algorithm if we actually do it on the graph. Okay, so let me fix this. Now, given that we've already converted the graph into its residual capacity, all we have to do now is to identify the different augmenting paths. So let me put here augmenting path, and let me put the flow or the augmenting path capacity. Okay, and then finally we will have total flow. on the right. Okay? Now, the first thing you have to do is identify an augmenting path. And let me do that for you. Let's say the augmenting path I identified is an O, A, B, D, T. Why is this an augmenting path? Remember the definition of an augmenting path? First, it is a directed path from source node O to destination node T. So looking at this augmenting path, it's a path from O to T. So yes. Second, are the capacities strictly positive? Let's look. The capacity of OA is 8. The capacity of AB is a 1. The capacity of BD is a 4. And the capacity of DT is a 9. Therefore, this path from O to A to B to D to T is an augmenting path. And the capacity of this augmenting path is the minimum, which is, well, in this case, you have to compare 8, 1, 4, 9. So the capacity of this augmenting path is a 1. And to be able to get the total flow, all you have to do is get the sum as of the last augmenting path you were able to identify. So in this case, the current sum is just 1. And because the capacity of the augmenting path is a 1, then we will let 1 unit go through this augmenting path. Okay? And because we will be letting 1 unit move, no, from O to A to B to D to T, then we can update these capacities, no, these residual capacities. Your 8-0 will actually become a 7-1. Okay? Your 1 and a 0 will actually become a 0-1. Your 4 and 0 will become 3-1. And finally, your 9-0, because you are letting 1 unit flow, will become an 8-1. So remember, you are decreasing in this capacity by 1, and you are increasing this capacity by 1. Okay? The algorithm requires us to exhaust all the augmenting paths available in the graph. So let me give you the second. Okay? The second is, for example, now there are a lot of augmenting paths, but let's say your second is an OCET. And what is the capacity of OCET? Let's look. 4, 4, 6. So everything is positive, so it's an augmenting path. But the minimum is a 4. Therefore, the capacity of the augmenting path is a 4. And because this is a 4, then the total flow as of the second augmenting path is a 5. And because we are letting 4 units flow through OCET, then this 4-0 will become a 0-4. This 4-0 will become a 0-4. And finally, the 6-0 will become a 2 and a 4. Okay, so let's just continue. Third, let us say the third augmenting path is an OBAT. First question, is this an augmenting path? Yes or no? Remember, there are two conditions, no, for you to see if a path is an augmenting path. First, it has to be a path from O to T. So yes, it is a path from O to T. Second, you have to make sure that the capacities are positive. So what's the capacity of OB? The capacity of OB is 7. What's the capacity of BA? 1. What's the capacity of AT? 1. So yes, this is actually an augmenting path where the minimum of 7, 1, and 1 is actually a 1. Therefore, the capacity of the augmenting path is a 1, and therefore the total flow is a 6. Now, before we move on and actually update, no, the residual capacities, let me point out first that you are letting one unit move from B to A. And why is that very important to note at this point? If you look at the original graph and look at the arc, no, between A and B, the arc between A and B actually has an arrow. And the arrow actually is pointing towards B, which means technically there shouldn't be, or you cannot let units flow from B to A. However, this is what I've been explaining a while ago, no, or what I explained a while ago, that in the augmenting path algorithm, where you already converted your network to the residual network, you can technically let units move back or flow back. And why is it possible to let one unit move from B to A in the first place? Because if you look at this augmenting path, OABDT, you actually let one unit move from A to B. And because you let one unit move from A to B, therefore, technically, in quotation mark, not technically, you can let one unit move back, no, from B to some node, and in this case it is a node going to um, A. No, it's a movement going to A. Okay, so let us update the uh, residual capacities. So we will let one unit move, so this 7 0 will become 6 1. This 1 0 will become 1 0, and finally this 1 0 will become 0 1. Okay, we can continue and identify other augmenting paths. So let's say the next augmenting path is an O, an A, a D, and a T. Capacities are 7, 3, 8. So the minimum is a 3, therefore the total flow is a 9. And if we let 3 units move, so O to A, we let 3 units, so this becomes 7 minus 3 is a 4. 1 plus 3 is a 4. Next, this 3 and 0 will become 0, 3. Finally, this 8, 1. So 3 units, 8 minus 3 is a 5. 1 plus 3 is a 4. Next, let's look for other augmenting paths. O, B, E, T. No? Obet. So that's a 6, 5, 2. Therefore, we have a capacity of 2 and the total flow is 11. Let's update. 6 1 becomes 4 3. 5 0 becomes 3 2. No? 2 4 becomes 0 6. I think there are still augmenting paths. Number 6, O, B, E, D, T. Capacity is a 4, 3, 1, 5. So 1. Okay? With a total flow of 12. And let's update OB. So this becomes 3, 4. BE. This becomes a 2, 3. Your 1, 0. No? Your 1, 0 becomes a 0, 1. And then finally, your DT, your 5, 4 becomes a 4, 5. Are there still augmenting paths? Yes. Let's identify. Number 7. O, A, B, D, T. And as you can notice, this augmenting path we've already identified before, no? And that's not a problem, no? As long as the path is a path from O to T and the capacities are positive, then this is an augmenting path. What's the capacity? 4, 1, 3, 4. So the capacity is 1, total flow of 13. So let's update. Your 4, 4 becomes 3, 5. Your 1, 0 becomes a 0, 1. This becomes, sorry, a 2, 2. And finally, your 4, 5 becomes a 3, 6. I think there are more augmenting paths. O, B, D, T. No? And the capacities are 3, 2, 3. So the minimum is a 2 and the total flow is 15. Updating the graph, we have your 3, 4 becomes 1, 6. Your 2, 2 becomes a 0, 4. And finally, your 3, 6 becomes a 1, 8. Are there still augmenting paths? What I'd like you to do is to pause the video and check for yourself if there are still augmenting paths. Okay. If you were able to check if there are still augmenting paths, I hope you were able to conclude that there are no more augmenting paths. And because there are no more augmenting paths, then we've exhausted all augmenting paths in the graph, and we can say that this total flow of 15 is our maximum or maximal flow. Okay? And what I'd like to do is I'd like to actually show you how the 15 units will flow through the graph. Okay? So let me graph first. Let me draw the graph first. So you have your O, you have your A, your B here, your C here, your D, E, and then T. Because of this maximal flow of 15, we know that 15 units will enter. And we also should be able to expect that 15 units will exit node T. The question now is how did the 15 units move through the network? Okay? All you have to do is look at every arc. In this case, for example, OA originally has an arc going to A with a capacity of 8. So remember, your OA originally has an 8-0, but because in the last network graph, OA now has the capacity of 35, then what does this mean? How many units actually flowed from O to A or A to O? In this case, from an 8-0 becoming 3-5, we can understand that 5 units flowed from O to A, no, with an arrow. Okay? In the same way, your flow from O to B is a 6. And your flow from O to C is a 4. And as you can see, the 15 units that entered node O was actually separated into 5 going to A, 6 going to B, and 4 going to C. Okay? Now, the 5 units that entered A, how did they go through and exit the network? If you look at AB here, it has a capacity of 0 and 1. What does that mean? That means 1 unit moved to B. In the same way, the capacity from A to D is a 0-3, which means 3 units moved to D out of the 5. And finally, the capacity from A to T is a 0 and 1. Therefore, we know that 1 unit moved from A to T. And as you can see, the 5 units that entered A moved this way. 1 unit moved to T, 3 units moved to D, and 1 unit moved to B. Okay? Now, if you look at node B, how many units entered node B? There's 1 unit moving from A to B and 6 units moving to from O to B. So that's a total of 7. In this case, how many units from B moved to C? If you remember, the capacity from B to C is a 2 and a 0, no? And because the ending capacity is still 2 here and 0 here, therefore we know that there are no units that traveled between B to C. If you look at the capacity between B and D, the capacities are 0 and 4. Therefore, we know that 4 units moved here. In the same way, the capacity between B and E is a 2 and 3, no? Therefore, we know 3 units moved to E. And as you can see, if 7 units entered B, no? If 7 units entered B, then 7 units also exited B. How? 4 units went to D and 3 units went to E. For C, 4 units entered C, and as you can see in the capacity, 4 units went to E. Okay? Now, looking at E, how many units went to E? In total, there are 7. And how did the 7 exited E? 1 unit went to D, and 6 units went to T because of these. And finally, how many units entered D? You have 3 plus 4 plus 1. That's a total of 8. How many exited D towards T? As you can see, there are 8. How many units entered T? That's a 1, 8, and 6. That's a total of 15. And that is why we have a maximal flow of 15. So given this set of augmenting paths, this is how the 15 units flowed through the network. Obviously, if you identified a different set of augmenting paths, then these capacities will be different. These total flows will be different, no? However, what will be the same is the ending total flow. In the end, no matter how you identify the augmenting paths, the maximal flow will always be 15. Your flow within the network might be different, no? Or will surely be different as you identify different augmenting paths. But what is sure is that 15 units will enter and 15 units will exit the graph. So how do we check for optimality in the augmenting path algorithm? The algorithm requires us to exhaust all the augmenting paths available in the network graph. It's a good thing that the example is a very small example. It just contains a very few nodes and arcs. But the problem is when we increase the number of nodes and the number of arcs, then exhausting the search, no, for all the augmenting paths will be very, very hard. Now, there is a theorem that we can use as an alternative to this augmenting path algorithm. Okay? And that theorem is called the max flow min-cut theorem. Before I discuss the theorem, let me first define what a cut is. A cut is a set of arcs such that if you remove or the deletion of which will cause flow from node O, the origin, to node T, the destination, impossible. So again, a cut is a set of arcs such that if you remove them, then movement from node O to node T will be impossible. The cut value is just the sum of the arc capacities of the arcs in the cut. Now, the max flow min-cut theorem states that for any network with a single source and destination node, the maximum feasible flow from source node to destination node equals the minimum cut value for all cuts in the network. So what's the significance of the theorem? If a cut of the network has a value equal to the total flow so far, then we are sure, or we can be sure, that the current total flow is optimal and maximum. So for example, in the example that we just did a while ago, and the total flow right now was 15, if we are able to find a cut that is also equal to 15, then we don't need to check if we've already exhausted all the augmenting paths, because if the max flow is equal to the cut that you found, then we are sure that the flow is already maximum. Okay? Now, in here, what I have is the example that we used. And let me give you one of the cuts available in the graph. Okay? So for example, one possible cut is an OA, OB, and an OC. Okay? Why? Because imagine removing these arcs. If you remove these arcs, then movement from node O to node T is impossible. Okay? And because OA, OB, and OC is a cut, therefore, their capacities 8, 7, and 4, which gives us a total of 19, is the cut value. It is the cut value of OA, OB, OC. Another possible cut is AT, DT, ET, with a cut value of 196. So imagine, remove this, remove this, remove this, flow from O to T is now impossible. The total of the arc capacities is 16. Therefore, this is the cut value of the cut AT, DT, ET. So the question is this 16 the minimum cut? Are you able to find a cut such that it has a lower cut value? Why is it important to find that cut value of 15? Remember, our total flow right now is equal to 15. And let us say, after looking for the different cuts in the graph, let us say so far the minimum cut you found is 16. So what does that mean? Does it mean this is wrong, or does it mean this is wrong? Unfortunately, the max flow min cut theorem will not be able to tell us which part of the analysis is wrong. We don't know if we missed an augmenting path such that the total flow will actually increase to 16, or we don't know if we were not able to find a better cut, a cut that is equal to 15. Remember the importance of having the min flow, the max flow and the min cut to be equal, because only when the two are equal can we be sure that the total flow that we have is actually the maximum. Now, if you actually try harder to find the cut, you will be able to see this cut in the graph. And what is the cut value? 1 plus 3 plus 4 plus 1 plus 6, a total of 15. And imagine removing these arcs. If you remove these arcs, then flow from O to T will become impossible. Therefore, this is a legitimate cut. And because the cut value now is equal to our total flow, then we can now conclude that this is actually the maximal flow. Unfortunately, the theorem also requires an exhaustive, in a way, an exhaustive search for the minimum cut. But at least if you are able to find a cut value that is also equal to the current total flow, then that gives us a way to be able to say that the total flow in fact is the maximum flow.